Welcome to The Explainer. Today, we're going to pull back the curtain on a hidden safety feature that works in fractions of a second. It's the one thing that stands between a stable power system and, well, a catastrophic failure, the short-circuit rating.
So to really get a grip on this, let's just start with a big question. What actually happens in those first few seconds of an electrical disaster? The answer is a whole lot, and it all happens faster than you can even blink.
So, let's meet the villain of our story, the short circuit. And this isn't some slow burn problem. It's a sudden, violent, bam, inrush of current. Think of it as an uncontrolled flood of electrical energy, way more than the system was ever designed to handle.
And when I say a surge, I am not kidding. We're talking a massive one. During a short circuit, the current can be 20 times, sometimes even more, than the normal, steady current that the cable carries every single day. That is an unbelievable amount of energy being unleashed all at once.
And get this, the entire event is a frantic race against the clock. The system's protection, like a circuit breaker, it has to kick in and shut down the fault, and it usually has less than 3 seconds to do it. The whole time, the cable just has to survive that incredible onslaught until help arrives.
So, how in the world does it survive? Well, it survives thanks to the hero of our story, the cable's own built-in defense mechanism. Its short-circuit rating. This is the engineered limit that really defines its strength in a crisis.
And here's the crucial point. The short-circuit rating is all about heat. It's the maximum current a cable can literally absorb for a few seconds without its insulation just melting or the conductor itself getting permanently damaged. It's really a measure of its ability to take a punch, electrically speaking.
The difference in scale here is just massive. Think of it this way. Normal current? That's like a calm, steady river, just flowing predictably along. A short circuit? No, that's a tidal wave, sudden, immensely powerful, and incredibly destructive if it's not properly contained.
But wait, it actually gets even more complicated. You see, the cable isn't just fighting off a wave of heat. That massive surge of current generates these powerful physical forces that are actively trying to tear the cable apart from the inside out.
You've got two main invisible attackers at work: thermomechanical effects, which come from that intense heat, and electromagnetic forces, which are generated by the current itself. Let's take a quick look at each one.
Okay, first up, thermomechanical stress. You know how metal expands when it gets hot, right? Well, imagine it heating up hundreds of degrees in less than a second. The conductor expands so fast it creates this powerful push, a thrust that can literally damage connections and supports if the cable isn't secured properly.
And at the exact same time, you've got these immense electromagnetic forces going wild. The huge current flowing through the parallel cores inside the cable creates these powerful magnetic fields that violently push each other apart. This creates a bursting force trying to rip the cable open. A lot of times, the cable's armor is the only thing holding it all together.
So, why does all this technical detail matter so much? Because the stakes are incredibly high. I mean, getting this wrong isn't just about things not working right. It's about preventing catastrophic failure, protecting property, and of course, ensuring people's safety.
Adhering to these ratings is just non-negotiable, and for some really key reasons. It prevents fires and explosions, it protects all the expensive equipment down the line, it's absolutely essential for making sure that breakers and fuses can actually do their jobs in time, and, of course, you've got to meet all the safety and regulatory standards.
And let's not sugarcoat what failure looks like. The source material puts it pretty bluntly. Exceeding the rating can melt the insulation, causing fires, explosions, or exposing live conductors. The consequences are, well, they're severe.
So if it's that critical, how do engineers actually figure out what a cable can handle? How do they calculate this vital safety margin? Well, it all comes down to a fundamental formula that acts as a kind of code for survival.
This is it, the standard adiabatic formula. It might look a little simple, but it perfectly balances the key factors that determine a cable's strength. I is the maximum current the cable can handle, and it's calculated using 3 key ingredients we're about to look at.
So, those ingredients are A, which is just the physical size of the conductor. Pretty simple. Bigger means it can handle more heat. Then there's T, the time the fault lasts, the shorter the better. And finally, K, which is a special constant based on the materials the cable is actually made from.
And this is where material science becomes absolutely critical. That K constant changes depending on the conductor, say copper versus aluminum, and the type of insulation, like high-temp XLPE versus standard PVC. Just look at this. An XLPE insulated cable can withstand a much higher temperature, 250 degrees Celsius. That gives it a significantly higher short-circuit rating. But here's the final, crucial twist in our story. Because having a perfectly rated cable, it's not enough. There's an often overlooked detail that can completely undermine the entire system's safety.
I mean, this quote from the source material just says it all. The method of installation and all the accessories, the joints, the terminations, the supports, these are often the weakest links in the entire chain.
At the end of the day, a system is only as strong as its weakest link. It's that simple. Remember that powerful bursting force and that huge push we talked about? Well, if the cable clamps or the terminations fail, the cable's rating is basically meaningless. The whole installation has to be designed to contain the forces of a short circuit.
Which leaves us with one final really important question to consider. It's not just about the cable, it's about the entire system. Is its safety built on a solid foundation of strength or on an overlooked weakness? Thanks for watching.